Welcome to day 2 of learning all material electronically. Today we are learning about energy. And our first question is, what is energy? So to learn about that, I ask you to think about how you could make a go-kart move. You have a go-kart here. Take a second and think about all the different ways you could make it move. Got a couple? Let's look at some of the ones I came up with. You could put this cart at the top of a hill and let it roll down. You could push the cart. Either get behind it and push it, or push it with your feet while you're in it. Put your hands down on the edge and push, and try not to run over your hands. You could put a gas motor on it. You can see one on here where the gas is exploding and turning into motion. You could put an electric motor on it, or maybe you could even wrap a rubber band or some sort of rope or stretchy rope around the axle, and as that rope compresses again, it causes the axle to turn. All of these things could make the cart move, and you may have come up with some more. Each of those things is an example of energy, a type of energy, because fundamentally what energy is anything that can cause motion. We're going to look at two main types of energy here, but we're going to focus on mechanical energy. Mechanical energy includes gravitational potential energy, spring potential energy, and kinetic energy. So to get the amount of mechanical energy, all we need to do is add together the kinetic and potential energies. There are other forms of energy, and we encounter these all the time. Heat is a form of energy. Chemical energy, such as gasoline, such as food. Gasoline is not food. Such as anything that you can combust and release the energy from. You probably remember that from chemistry. And electrical energy, voltage, essentially. You should know that energy cannot be created or destroyed. Instead, one type of energy becomes another type of energy. You probably learned about this in physical science in 8th grade. Energy turns from one type to another. An example we've talked about before is rubbing your hands together and that kinetic energy turning into thermal energy. Here we have all sorts of different types of energy listed over on the right, and you could think about, for example, you could eat food, which is chemical energy, and then you could go for a run, which is kinetic energy. So essentially what's happening is that chemical energy is being turned into kinetic energy. Here we have a man turning kinetic energy into thermal energy by rubbing the piece of wood on the other piece of wood. That friction is heating it up, and he's hoping to create a fire. Here we have a walker falling to the ground. That is potential energy, the energy of height, turning into kinetic energy, right? It speeds up as it falls. Here we have kinetic energy, the speed energy, as the man's immediately thrown up from the tarp, and then it turns into potential energy as he moves upward. Notice that at his highest point, he stops for just an instant. As he stops going up and starts going down, that's where his kinetic energy is 0 and his potential energy is maximized. As he falls, that potential energy turns back to kinetic energy. Oh my. This man goes so fast at the bottom. He has so much kinetic energy. Where did that kinetic energy come from? Well, didn't it come from his potential energy? He started so high up that he had plenty of potential energy, and that potential energy turned into kinetic energy as he slid down the rail there. If he started higher, he would start with more potential energy, which would turn to even more kinetic energy, which would mean he would go even faster and produce even more laughs. This man is turning chemical energy into kinetic energy. I assume that he's put a Mentos into that Diet Coke bottle, and so a chemical reaction is occurring, which is causing the bottle to fly through the air. This man is allowing a mass to fall on a pendulum on a string, and he's standing up against a wall so that if it makes it back to his head, it'll knock all his teeth out. But of course he knows it won't, because energy is conserved. The amount of energy that that ball starts with, the amount of potential energy, even though it's changing to kinetic energy, back to potential energy, back to kinetic energy, back to potential energy again, he knows it will end up with the same amount or slightly less energy than he started with. Where did that extra amount go to? That would be to friction. Some of it's turning into thermal energy as the joint turns up there at the top where the wire is bolted to the ceiling. This boy is going to go through the same demo, and notice it never makes it back up to his head. But of course, it did keep going. Here we have a fire, which is chemical energy turning into thermal energy. Those chemical bonds break. And here we have a man falling to the ground with a parachute. That parachute is doing negative work on him. In other words, it's slowing him down, providing an upward force as he moves downward. That's negative work. Let's talk about the three main types of mechanical energies. The first one is kinetic energy. Kinetic energy is the energy of movement. The formula for kinetic energy is 1/2 mv squared. Notice the v is squared. That means that if something goes twice as fast, it has 4 times as much energy, which we can see in this bottom the bottom right video of the railgun. This is not an explosive projectile. All those flames, all that bursting thermal energy and explosion there is all caused by the kinetic energy of that little object. It's moving so fast that it causes all that destruction, even though it's fairly small. All energy types are scalar, and in this case, velocity is a vector. So how do we end up with a scalar? Well, when you take a vector and you multiply it by itself, we end up with something called a dot product. And you may remember that from algebra. A dot product is a scalar. So it doesn't matter what direction something is moving in, it's going to have the same kinetic energy if it's going the same speed and has the same mass. Here we have potential energy of gravity. So Superman is going up the escalator. He is gaining potential energy of gravity, right? He's getting higher. That means that something must be doing positive work on him. Something is giving him that energy. That's the escalator. It's pushing him upward and he's moving upward. So it must be positive work, so he gains energy. The formula for gravitational potential energy is mass times gravitational acceleration times height. So we don't know Superman's mass, but gravitational acceleration is 10 or 9.8, and then the height is however high he's getting to. This produces the total gravitational potential energy. If instead he were on the moon and he went to the same height, there would be less gravitational potential energy because the gravitational acceleration on the moon is less. If he goes twice as high, h will double and therefore we'll end up with twice as much potential energy. And again, this is scalar. Over on the right, you see a man leaping up the stairs. This is very important. I want you to see that no matter how fast he goes up the stairs, because he starts at the same height and he ends at the same height, he's gaining the same amount of energy. Again, he starts from the same height, ends at the same height, so he must be gaining the same amount of potential energy. If he walked up those stairs, he would gain the exact same amount of energy. And therefore, it must take the same amount of work to go running up the stairs, to go leaping up the stairs, or to just walk slowly up the stairs. Because work is the change in the amount of energy, and he's gaining the same amount of energy. So what's different from the way he's bounding up the stairs now? It's that he's generating more power. If he walked up the stairs, he would do the same amount of work, but generate less power. And finally, we have spring energy. Spring energy is simply the energy of an object being deformed and wanting to return to its natural shape. You can see Merida down at the bottom. She's pulling a bow back, bending that bow back, and the bow wants to move back to its original shape. And in order to do so, it pulls that string, which causes that arrow to go flying. The formula for spring potential energy is 1/2 kx squared, where the k is the spring constant. That's just a number that represents how stiff the spring is. So for example, on a car, you might have a really large spring around a strut. That's going to have an extremely high k value. Whereas in your mechanical pencil, you have a tiny little spring. That spring has a very small k value. X is the distance that the spring is compressed or stretched, or the distance that the bow is bent or a piece of PVC is bent or whatever. Notice that if you stretch the spring twice as far, you get 4 times the amount of energy. Or if you compress a spring twice as far, you get 4 times the amount of energy. And I'm sure you felt that if you've ever compressed a very heavy spring. It's so much harder to get it to compress further once you've got it halfway compressed already. Take a look at this transition of energy. As Merida pulls back the bow, that spring energy is being passed into the arrow as kinetic energy. So one type of energy turning into another type. The amount of mechanical energy stays the same because spring energy and kinetic energy are both mechanical energies. So we have the same amount of mechanical energy, the same throughout this whole animation, but it starts with spring energy, and that spring energy turns into kinetic energy. If you take a look at the slinky on the right, you can see the mechanical energy is staying relatively the same as the potential energy, gravitational potential energy, is turning into spring energy. Again, this is a scalar because though there is displacement with that x, it is multiplied by itself once again as a dot product. Make sure you know your types of energy. Make sure you know what mechanical energy is and that it is the sum of gravitational potential, spring potential, and kinetic energies. And make sure you know that energy is conserved. Again, let me know if you have any questions after doing the reading and watching this.